my talk, as has already been mentioned, is joint work with Roman. And the question or the topic is, you see it in the title, the Boltzmann equation and its place in the edifice of statistical mechanics. Quick overview what I will do. So there will be an introduction where I introduce the questions, then I will introduce the frameworks that we need, Boltzmann and statistical mechanics, Gibbsian statistical mechanics, and the Boltzmann equation. Then we talk about the relation between the Boltzmann equation and Boltzmann statistical mechanics. Then we turn to this alternative derivation of the Boltzmann equation within the framework of the BBGKY hierarchy. And then we talk about this Boltzmann equation, the BBGKY's Boltzmann equation and the relation to Boltzmann and Gibbsian statistical mechanics. And then I will conclude. But the topic is really, as is in the title, to see how the Boltzmann equation relates to Boltzmannian and Gibbsian statistical mechanics. Okay, introduction is really about introducing the question. So the question, so the large project is, what is the relation between different strands of statistical mechanics? And of course, as you all know, and there have been talks about that in these workshops as well, it's common to present statistical mechanics as consisting of two broad theoretical families, Boltzmann and statistical mechanics on the one hand, and Gibbsian and statistical mechanics on the other hand. So if you look into books about statistical mechanics, foundational books, or compendia such as Jo's compendium on the foundations of statistical mechanics, you always see this division into Boltzmann and statistical mechanics and Gibbsian statistical mechanics. But statistical mechanics is, of course, more pluralistic than that. There's more. There's also the Boltzmann equations. There is also the Boltzmann equation, and of course also many other transport equations. But this talk is really about, as I already said, how does the Boltzmann equation fit into the Boltzmann and statistical mechanics and Gibbsian statistical mechanics. So, this is the question. I want to motivate that question a bit further. So one might think, you might say, well, it's the Boltzmann equation, there's the name Boltzmann, the Boltzmann equation. So isn't it obvious that the Boltzmann equation is Boltzmannian and so belongs to the framework of Boltzmannian statistical mechanics? But it's not obviously true because the Boltzmann equation, though the name Boltzmann is in it, is different from the framework of Boltzmannian statistical mechanics. In particular, look at the second bullet point now. So they're also formulated in different or discussed in different papers historically. So Boltzmann formulated the Boltzmann equation in 1872 and then started afresh in 1877. And it's the 1877 paper that lies at the foundation of Boltzmannian statistical mechanics. So historically, we have these two papers, and historically, so it suggests that there are two different approaches, or at least it's not clear that they are the same approach at the very least. Yeah. Also, in the famous Ehrenfest review on the foundations of statistical mechanics, they present the Boltzmann equation under the heading, the older formulation of statistical mechanical investigations, and then move on to discuss the 1877 approach in a new section entitled the modern formulation of statistical mechanical investigations. So again, this really presented as two approaches. So historically, the Boltzmann equation and what we now regard as Boltzmannian statistical mechanics are rather seen as distinct approaches, or at the very least, they're not regarded obviously as the same. Okay, but of course, if you look at contemporary literature, there's a lot of work on Boltzmann and Gibbsian statistical mechanics, but there's of course also a lot of work on contemporary literature on the Boltzmann equation. And it's definitely not set aside as an old formulation, but it's a subject that is very much alive. But when you look at the literature on the Boltzmannian statistical mechanics, it largely ignores or doesn't talk so much about the Boltzmann equation and vice versa. It's more that the Boltzmann statistical mechanics and the Boltzmann equation are practiced side by side, and there's little discussion on how the two relate. So we can at least, I think it's an important question to ask, how exactly do they relate? So how do the Boltzmannian, how does Boltzmannian statistical mechanics and the Boltzmann equation relate? So this is the first thing, Boltzmann equation, how does it relate to Boltzmannian statistical mechanics? And then, of course, there comes the question, how does it relate to Gibbsian statistical mechanics? So this is on the next slide. So likewise, how do the Boltzmann equation and Gibbsian statistical mechanics relate? Boltzmann equation doesn't, at least if you look at it, doesn't seem to fit into Gibbsian statistical mechanics either, at least not Boltzmann's original derivation. But, and that is interesting, as we all know, there's also an alternative derivation of the Boltzmann equation in the BBGKY approach. And there was a suggestion, or there is a suggestion out there in the literature that this is something like a Gibbsian version of the Boltzmann equation. And this is something we also will discuss. So is it really? And answer will be, as always, complicated, depends on what you mean by Gibbsian statistical mechanics, but we will at least voice also some skepticism. Okay, I mean, this is about the motivation of the question, really, how does the Boltzmann equation relate to Boltzmann and statistical mechanics and to Gibbsian statistical mechanics? Okay, now we have a large section where we need to introduce the protagonists. This is, of course, Boltzmannian statistical mechanics, and we need to introduce Gibbsian statistical mechanics, and then also the Boltzmann equation, and also the two derivations of the Boltzmann equations. Okay, we start with background. I mean, the background is important for all these approaches. That what we are working is in the framework of, in a way, dynamical system theory. So we don't look at it quantum mechanically. We work with the classical approach, and there you have a dynamical system consisting of a state space. So we call that state space. Sometimes it's called phase space. It doesn't really matter. You just have to be consistent with the terminology. We talk about state space X, and this is really a set of all possible microstates. Yeah, set of all possible position and velocity coordinates of a gas, for instance. And then I'm very much aware that usually, then you also have a sigma algebra, and you have this measurability constraints. So I will assume throughout the talk that functions are measurable, etc., but won't really talk about sigma algebras here because I'll try to keep it simple. Yeah, but I'm very much aware that this is in the background. And all we say here makes sense in the context of measure theory. So you have a state space, as I said, really think about it intuitively as a set of possible microstates. Then you have a measure on it. That is, in statistical mechanics, usually invariant under the dynamics. Think about something like the microcanonical measure. Can be other measures as well, but to have an example, it makes sense. Think of the microcanonical measure. And then an evolution equation, where TTX is the state of the system after t time steps that started in x. So small x is a microstate, yeah. Capital X is the state space, and small x is a microstate. And when you evolve that microstate, the TTX gives you the state of the system after t time steps that started in x. And usually, of course, the evolution equation in our context derives from the Hamiltonian dynamics. This is just common ground, background to everything that I will say here. And now to Boltzmannian statistical mechanics. So historically, of course, what's very important is the combinatorial argument. And the standard account is that in the combinatorial argument, that macrostates are elements of a partition of state space. As I said, historically, often individuated to Boltzmann's combinatorial arguments. So when you read introductions to Boltzmann's statistical mechanics, of course, the combinatorial argument is something you will often read at the very beginning. And that's presented as the way macrostates are individuated. But there is a worry. I mean, if you only focus on Boltzmann's combinatorial argument, that is not general enough. What I mean by that is Boltzmann's combinatorial argument is about a very specific setup, very dilute gases, but we want to talk about macrostates in statistical mechanics in many contexts, not only about very dilute gases, but for instance also about the Ising model, which is not, of course, a very dilute gas, etc. So there's the worry that Boltzmann's combinatorial argument first is not general enough. There's also the worry that some voice that there's the question, what is really macro about that? Yes, we have a partition, but how is that partition motivated? And so what Roman and I mean, this is really past work, but what we have done is to present a more general account where what Boltzmann does, the combinatorial argument, is really a special case. So where we say, what are macro variables? Well, macro variables are simply functions. VE from X to another space, which we denote here by capital VE. So it is a function. Macro variables are simply functions from state space X into another space. And a particular set of values, defines then a macro state, which we denote by V1, Vl. V1, Vl are can be, I mean, L is just a natural number. It's just a number of macro states. Yeah, you can macro variables you consider that defines macro states. And then what you do is you, of course, want a partition of state space, but these macro variables give you a partition, namely by supervenience. Every macro state M is associated with the macro region, which we call XM, consisting of all microstates for which the system is in M. So in essence, what you have, I'll give you a picture in a moment. You just look at state space and then you partition it into different regions dependent on the macro variables, the macro values you have. And one of these regions, of course, is the equilibrium region, and that is then the region that corresponds to the equilibrium macrostates. There are different definitions of equilibrium available. I mean, Roman and I have defended one particular version of it. We don't really have to go into details here because it won't really matter much for what will follow. But just that you have the intuitive idea. The idea is, of course, that the system spends most of its time in equilibrium, and also that equilibrium is the largest state. So these are these two ideas about equilibrium. And the approach to equilibrium, of course, is understood as the system states evolving into an equilibrium macro region. So I have this picture, so where everything that I said about Boltzmann and statistical mechanics and macro states and equilibrium is really shown in a picture. So what do we have here? So that blue-gray area here is state space, and you have that state space is partitioned. You have a partition here. You have M1. Here you have M2, for instance. Here M3, M4, M5, and then you have M. That's the equilibrium macro state. At the equilibrium macro region. Sorry. Of course, you have usually much more macro state. So this is simplistic, but you see how it works. The state space is partitioned into different macro regions. And these macro regions correspond to different macro states, macroscopic states of the gas. For instance, here we have M1, where the particles are all on the right-hand side of the gas. And here we have the equilibrium region where everything is spread out. And of course, what you have, I mean, this is really Boltzmann and statistical mechanics in a picture. What you have is that you consider the evolution of trajectories, of this TTX, what I had in dynamical system theory. You start with an initial x0, and then it evolves forward. And the idea, of course, with equilibrium is that it evolves into the equilibrium region and stays there most of its time. So that's, in a nutshell, Boltzmann and statistical mechanics. And now we turn to Gibbs statistical mechanics. In Gibbs statistical mechanics, of course, the core object that one considers is a probability density or a distribution, and denoted often by rho xt, so time-dependent over state space. And usually you have that this is interpreted as an ensemble, so that rho xt is the probability of finding the system in a certain region R of state space at time t. So when you take the integral, then you rho xt integral over R is then the probability of finding the system in a certain region of state space at time t. So you can use this probability and density to calculate probabilities of the system being in a certain region. And then, of course, the concept of equilibrium, as we all know, is very different from the one in Boltzmann and statistical mechanics. We have that, so rho xt is stationary, and the definition we need for equilibrium. So rho xt is stationary if it doesn't depend on time, and then you have that an equilibrium corresponds to a stationary distribution. Sometimes you have further constraints, doesn't really matter here. But what is important, I think, is that in Gibbs statistical mechanics, equilibrium is a property of an ensemble. Very different, of course, to Boltzmann. Then observables are real valued functions, f on state space X, and then you have this what is called the averaging principle, and much contested averaging principle. So we have spent countless hours discussing this, and Roman and I with colleagues what the exact status of the averaging principle is in Gibbsian statistical mechanics. Very contested, but I think it's fair to say that many say that what we usually some say we always observe an equilibrium phase average. Some just say usually. Doesn't really matter for today's talk. But what is important that there is, of course, this averaging principle that says, well, what we observe in experiments are phase averages. And what is a phase average? I mean, I have the definition here in equation 1, but intuitive, in essence, what you do is just you average over the observable over state space. Phase averages from phase space. As I said, you can either call it state space or phase space, but what the averaging principle does is really average over phase space. And that's what equation 1 does. So you have fxt, rho xt. And I'm sure in the workshop you have already discussed a lot about that, but there are, of course, many interesting questions concerning the exact interpretation of Gibbsian statistical mechanics. And we have a paper on that in BJPS in 2021, and I know David is doing some work on that as well, which will, I'm sure, give rise to interesting discussions. Okay, then what we have now introduced Boltzmann in statistical mechanics and Gibbsian statistical mechanics, and we need a Boltzmann equation. So here we go. So in Boltzmann's 8072, you have the Boltzmann equation, the H theorem. It's this famous paper by Boltzmann. And what does he do? I'll try to summarize here the really complex argumentation. So you have a time-dependent distribution function. That's extremely important. The focus is really on this distribution function, ft v, for the relative number of molecules with a certain velocity at time t. So you consider the relative number, just to say it again, of molecules with a certain velocity at time t, and this is a distribution, of course. And Boltzmann's aim was to show that over time, an initial distribution, so originally I wanted to show that any initial distribution over time approaches the Maxwell-Boltzmann distribution. And what does he do specifically in the paper? So he considers a monatomic gas of elastic hard spheres of diameter d, and assumes, that's of course very important, you might have immediately thought about, well, the distribution function that isn't the continuous and differentiable function. And of course, no, the exact distribution function isn't. That's discrete function with many jumps. But what Boltzmann assumes is that the number of molecules is sufficiently large so that the discrete velocity distribution can be approximated by a differentiable function. So this is when the number of n goes up, so then we can approximate it by a differentiable function. Then, of course, there is this famous Stoßzahl-Ansatz that is really absolutely crucial for the derivation in that paper. And the dynamics results from the Stoßzahl-Ansatz. So he assumes that the number, what does the Stoßzahl-Ansatz say? So it's really about the number of collisions, makes it dependent on the velocities. So the ansatz says that the number of collisions during a time dt in which the initial velocities are changed into final velocities within a spatial volume element is proportional, this is not a crucial bit, to the product of the number of particles with velocity v1 and those with velocity v2. So the number of collisions are made dependent on the number of particles with velocity v1 and those with velocity v2. The Stoßzahler answer is assumed to hold also in the reverse temporal direction in that paper. And furthermore, he makes a couple of further assumptions, which I just will summarize briefly, the main assumptions that also go in, namely that each direction of velocity is equally probable. He also assumes that the relative number of molecules with a certain velocity does not depend on their positions, and that the density of the gas is low, so that only binary collisions matter. So you see there are many assumptions. Yeah, the density of the gas is assumed to be very low, but yeah, all those assumptions are of course crucial, but particularly crucial is of course the Stoßzahler ansatz. And then under these assumptions, he derives an integral equation known as the Boltzmann equation, which we have here. And yeah, that's the original derivation of the Boltzmann equation. As we'll see later, there's also a very different derivation within the BBGKY approach, but this is what I will refer to as the original Boltzmannian derivation of the Boltzmann equation. Okay, so now we have introduced the protagonists. That's great, and so we can move on to the discussion to see how these different relations are. And first, we turn to the relation between Boltzmannian statistical mechanics and the Boltzmann equation. A comparison between the Boltzmann equation and Boltzmannian statistical mechanics will have to focus on two issues, namely on states and dynamics. I mean, the states, the first question, of course, is how are the states of a system described in both approaches? And I don't only mean microstates here, but also the macro approach. And how do these descriptions relate to each other? And then there's the dynamics. How are the dynamics of the system described in both approaches, and how do they relate to each other? Initially, when you look at them, I think, at least my feeling initially when I looked at them was that, well, initially they seem rather different. The dynamics seems different. The states seem to be described differently. But then there seems to be also at least some similarity in thinking about macrostates, and we'll spell that out now. So first, focus on states. So how are the states of the systems described in both approaches, and how do the descriptions relate to each other? And recall, I mean, this is just what I said when I introduced macrostates. I told you there's this combinatorial argument, and I told you that it's not general enough, and there's the worry about what the combinatorial argument really gives you in terms of macro properties. And then that we have, Roman and I have developed this alternative account where macro variables are simply functions. Functions VE, of course, everything measurable from state space X and another space, capital V. And that's very general because the capital V can be anything, really, I mean, any well-defined mathematical space. We'll come to that later. So we have functions VE, and they can, of course, a finite number of functions that can be different for each E. And that's just to recall what I already said before. That was this idea of macro variables that then partition the state space. You can also recall the picture I showed you then. And now it will be important to introduce this distinction between global and local variables. So we discussed it in a paper in 2023 that Roman and I have written. Global variables are ones that assign a value in the real numbers to the entire system. So I'll give you a very simple example where it will be clear what I mean. So think about the Ising model and the total magnetization. Yeah, what you will do here, of course, you take a microstate of the Ising model, and what you get out is the total magnetization, which is simply a number, a natural number, because you just count how many ones are there. Yeah. So what you get is that that global variables, we call it global variables, assign a value and the real numbers to the entire system. So your VE are simply the real numbers. And typical, like magnetizations, you could also think of total energy, but the magnetization is a very simple example of a microstate. And what you get as a macro value is a number in the real values. Local variables, here it becomes more complicated. They also fit within our framework, but they assign values to each point in physical space. So the way Roman thinks about it is really, this is the example of local pressure that Roman likes. So think about a gas, and the gas is, of course, in real, happening out there in real space. And then you think about local pressure about a point in physical space, and a ball around that point. And then you wonder, you ask, what's the pressure in that point, in that ball around that point? And that's Roman's example of local pressure. And of course, in non-equilibrium situations, local variables, so the local pressure, will not assume the same value everywhere, but will be different on where you look in the gas. The local pressure here will be different from the local pressure over there. And what's important here is that local variables assign values to each point in physical space. So what you have is that for local variables, your VI, I said before that VI can be really anything that is defined, that makes mathematical sense. And here VI are scalar field configurations. What's that? I mean, scalar fields, as you know, are functions from R3 to R. And so what you have here is these local variables are scalar fields. More particularly, what you do is you consider the set F of all scalar fields. I mean, all, of course, measurable, well-defined fields on R3. And then for these local variables, VE is the set of all scalar fields. And macrostates are individuated by real values. No, sorry, let me stop there. So I think maybe back again to, sorry if emails come in. So global variables, think about the magnetization example. Local variables really assign to a microstate a function. Yeah, that's the important thing. And scalar fields, I mean, the function of scalar fields, when you think about variables that assign values to each point in physical space, you have scalar fields. That nicely fits into our framework as well. It's just a bit more complicated because the VE space VE is the space of all scalar fields and not just the real numbers. But apart from that, nothing really changes. So for macrostates, that's the both point here, and they are individuated by real values, of course, for global variables, and for by field configurations for local variables. Supervenience holds here in the same way. You get again a Boltzmannian partition on the state space in a proper macro way. And now comes the crucial bit. I mean, why do I talk about these local global variables? I talk about it because it's crucial for relating Boltzmannian statistical mechanics to the Boltzmann equation. Namely, we need one further step. So far, the fields we have considered were scalar fields. So like the pressure distribution, the example that I introduced that Roman likes. But mathematically, that's of course not necessary. You don't need to restrict yourself to R3, but you can associate the field over any space within a point in X. So mathematically, what you need for this macro framework that we developed is that a microstate X gets assigned the function. Yeah, macrostates are functions. Gets assigned something. This something can be doesn't need to be a scalar field. It can be any function. Yeah, and now this is crucial because I highlight this is that this is what the Boltzmann equation, the distribution function in the Boltzmann equation does. So what does the distribution function do? You have a microstate X, and to every microstate, yeah, you have a gas, of course, in front of you that corresponds to that microstate. and that you get a distribution function, yeah, a function assigning giving you the relative frequency of the different velocities. So what you have is an x gets each microstate is assigned, so to speak, a distribution function, a function. So every point in x is assigned a function, a field over the one particle velocity space, and hence the velocity distribution in the Boltzmann equation has the same kind of structure as local field variables in Boltzmann and statistical mechanics. So that's why we have talked about local and global variables, because what you have here is really that in the Boltzmann equation, microstate x gets assigned a function, namely the distribution function, and that fits neatly into the framework we've developed if you generalize it to that. Because the VE, as I said, can be anything that makes really mathematical sense and physical sense, of course. So in essence, we have here that the state description in Boltzmann and the state description, the Boltzmann equation that focus on the distribution function is of the same kind as our reformulated version of Boltzmann and statistical mechanics. So you see that that's also why I have the title, same kind of state descriptions. So and I think there's also an intuition you have when you initially look at the Boltzmann equation and Boltzmann and statistical mechanics. You have the intuition that there's something that these frameworks share, and I think this something, in part at least, is that they have the same kind of state descriptions. Okay, then we have states. We've discussed states. We'll turn to the dynamics. What about the dynamics? The dynamics is complicated, of course. Note, let's start that every point x in the n-particle space x has a unique velocity distribution. That's clear. So moving a state x forward in time and then determining the velocity distribution. And when moving a velocity distribution forward in time, FTV are different description of the same thing. So that's what the Boltzmann equation wants to do. And this is, when you think about that, then of course immediately you think about Lanford's theorem, which we won't now discuss in detail. But Lanford's theorem then really, of course, shows you that there's consistency about it. So that moving a state forward in time and determining the velocity distribution, and moving a velocity distribution forward in time under the Boltzmann equation are one wants them to be the same thing. But the dynamical laws are, of course, different. So when you look at the original derivation of the, let's start with Boltzmann and statistical mechanics. Yeah, in Boltzmann and statistical mechanics, the dynamics is clear. It has to come from the fundamental Hamiltonian equations. This determines then your TT, this abstract TT in dynamical system theory. And the Boltzmann equation, it's different because you have a lot of assumptions. We have discussed them. But the dynamical law is very much based on the Stoßzahl-Ansatz plus this actually many auxiliary assumptions, and no direct appeal to the fundamental Hamiltonian dynamics is made. That's also the interesting bit about the Boltzmann equation. The original Boltzmann's derivation, ingenious because he manages to derive this equation with lots of assumptions, yes, but the Stoßzahl-Ansatz plus these other assumptions does suffice to so to speak, for him to derive the Boltzmann equation, which is interesting. We know, as I already said, we can discuss Lanford's theorem later if you want, but we know from Lanford's theorem that they are consistent for at least 40% of mean collision time. What we mean by consistency is, of course, you ask, I have the distribution function, I move it forward with the Boltzmann equation. Is this the same thing as really looking at state x, evolving it into the Hamiltonian dynamics to xt, as a t time step forward, and then looking at the distribution of state? And Lanford theorem at least tells you that there's consistency in the sense that for 40% of the mean collision time, many initial conditions, not all, a lot of, we can come to that in the question section if you're interested. Lanford theorem, of course, doesn't tell you that all initial conditions are like that, but at least that many are like that, and that there's at least, in many cases, consistency between the Hamiltonian dynamics and the Boltzmann equation. So Boltzmann equation is an approximation to the true Hamiltonian dynamics. The dynamics is different in the two approaches. I have a summary here, but there's at least some consistency. So what really summing up, what are the relation between the Boltzmann equation and Boltzmann and statistical mechanics? First, the Boltzmann equation fits neatly into the framework of Boltzmann and statistical mechanics in the following sense, that the state description in the Boltzmann mechanics can be construed as being a special case of our reformulated version of Boltzmann and statistical mechanics. And that dynamically, if one is optimistic, then the Boltzmann equation can be seen as an approximation of the Hamiltonian dynamics. But of course, one has, so the question about scope, the Boltzmann equation uses one specific macrostate structure, while the Boltzmann and statistical mechanics framework, of course, is more general. That's not a problem, it's just a remark, yeah. Boltzmann equation naturally just focuses on one specific macrostate structure, while Boltzmann and statistical mechanics in general wants to encompass all kinds of macrostate structures. And we have the position is not part of Boltzmann's original discussion. This is just a remark, also no problem. Okay, so much about the Boltzmann equation and Boltzmann and statistical mechanics. And now, in order to be able to talk about the relation to Gibbs statistical mechanics, we need the second derivation of the Boltzmann equation, namely the derivation of the Boltzmann equation in the BBGKY approach, that is completely different to Boltzmann's derivation. One focuses also on different entities, as we see. And it's also quite complex, but I'll try to present it in a simple way. So what is the BBGKY derivation of the Boltzmann equation? So what one does is one considers an n-particle system where the Hamiltonian, so these are simply the assumptions that go in for later arriving at the BBGKY hierarchy. So one considers an n-particle system where the Hamiltonian has no terms that depend on more than two particles, and it's also assumed to be symmetrical under particle permutation. And then one has what's in equation 2, this Hamiltonian, where you here sum over the pi squared divided by 2m. Then you have a term where capital V is the potential that represents the walls of the container, and you sum over V qi, and then you have this term where phi is the interaction potential between particles, and you assume that the Hamiltonian depends on not more terms than two particles, and yeah, I think that we then you arrive the Hamiltonian has the form of equation 2, and then you assume that's crucial in the BBGKY derivation that you have a probability density rho t x on state space. So we have a probability density, and the density, of course, evolves in the normal Hamiltonian framework according to the Liouville equation that we all know. This is equation 3. It's crucial, really, that you start with the probability density. And now with the density, you are looking at the marginal distributions, and I will come to that. So, a note, the symmetry of the Hamiltonian per se, this is always emphasized also on the derivations of the BBGKY hierarchy, the symmetry of the Hamiltonian does not imply anything about the symmetry of your rho t, but the BBGKY hierarchy restricts attention to symmetric rho t, in other words, assumes that rho t is symmetric. And then what you do is that you consider the marginals. The marginals, as they're simply defined in probability theory, for us particularly important will be this rho t1. That what does rho t1 do? It really looks at rho t, integrates over it over all variables except the first one. So what this does is, so to speak, it gives you the probability of finding one particle in a certain state, of finding one particle in a certain state, so independently of the others, because the others are conditioned on. So this is the first marginal, and what generally, maybe let's go to the second slide where I have it in words. So rho t1x1 is simply what I have intuitively described now, the probability of finding one chosen particle in a state while all other particles occupy arbitrary states. This is in words what the definition of a marginal here does, and particularly important, as I said, will be this rho T1, where the probability, where you consider the probability of finding one chosen particle in the state. So it's really intuitively, you can think about it just as the probability of finding one arbitrary chosen particle in a certain state. That's what the marginal gives you, the first marginal. You can, of course, generalize this and not only look at the first marginal, but look at, so maybe go back. Here you have, you consider x1 to xi and integrate over the remaining x1, xi plus 1 xn. And what this, of course, then gives you is the probability, here we are, of finding one chosen set of I particles in the state, while all remaining particles occupy arbitrary states. So you have these marginals that you can consider. And these marginals are now crucial in the BB-GKY derivation. Namely, one can then derive equations of motion for the one particle marginal and for the higher order marginals. I've written it down. I don't think you have to understand everything here. If you haven't already studied the BB-GKY hierarchy, it's complex. I've just written it down that you see how it works. You can derive equations of motions here for the one particle marginal. What's crucial is that you can derive these equations for the one particle marginal and for the higher order marginals, and that these equations are not closed. So I think this is what you should understand. If to get rho T1, you need rho T2. To get rho T2, you need rho T3, and that's where the name hierarchy comes from, BB-GKY hierarchy, because you have this hierarchy. And maybe not surprisingly, when you have that hierarchy, you wonder, how can I solve the equations? And solving the equation is initially as difficult as solving the original Hamiltonian equations. But what you can do is, of course, to cut off the hierarchy at some point. If you cut it off at some point, things become easier. And in particular, the simplest case that is often considered, and that will lead us to the second Boltzmann equation, so to speak, and formulate the same but interpreted differently. Namely, the simplest case is when I is just 2, and in this case, you and the assumption, so I is equals 2, and you have the assumption that rho 2 factorizes into the distant past. So what you do here is, as I said, you have to cut off the hierarchy, and what you do here is to represent rho T2 in terms of rho T1. Yeah, this is, and you have cut off the hierarchy in the simplest way, so to speak. And one way to do it is really what's stated here in equation 8, that you say rho T2 as t goes to infinity, to minus infinity, sorry, just factorizes into rho T1 and rho T1 x1 and rho T1 x2. Then you have expressed rho T2 in terms of rho T1. Intuitively, 8 has something to do with the Stoßzahlenansatz. Yeah. What you assume here is that the molecular states of any pairs of particles are uncorrelated before their interaction. So you have some kind of analogy to the Stoßzahlenansatz. And of course, this 8 is crucial. So you have the BB-GKY hierarchy. You cut it off at some point. In the simplest case, I equals 2. And this assumption. And what you get then is, as you will already suspect, in the end you get the Boltzmann equations, but you need some further assumptions. So you need the assumption that rho T2 is uniform over the position coordinates. It's clear that you need an assumption like that. Otherwise, you won't arrive. I mean, the key, the focus then will be on the velocity coordinates, of course. And you need the assumption that you have a finite range interaction potential. And then what you get is that rho T1 satisfies formally the Boltzmann equation. Yeah, you have an equation, then for rho T1, and that is mathematically simply equivalent to the Boltzmann equation. But of course, I mean, that's quite important. That's also the Boltzmann equation mathematically, but formally the interpretation is quite different. Because for Boltzmann, you interpret, I mean, I'm now here, in Boltzmann's original derivations, you have, of course, that this FTV is the distribution function. Yeah, but not in GQY's derivations. It's not the distribution function, it's the one particle marginal distribution. That's really a different thing. Yeah, they're different objects. That's why I have this in blue. So note that BBGKY's rho T1 and Boltzmann's FTV are really not the same, they're different objects. FTV is a relative frequency distribution, as I already said, and rho T1 is a one particle marginal probability distribution. You can discuss how you want to think about that more specifically, but a chance for one particle to be in a certain state. This is how you can intuitively characterize it. So you have anyway two Boltzmann equations. They're formally, it's the same equation, but here in interpretation is about different things. And Boltzmann original approach is about the relative frequency distribution, and the BBGQY's derivation is about the one particle marginal probability distribution. Okay, I know this BBGKY approach is quite complicated, but I hope what you could take away from it is that there exists this hierarchy, yeah, that you can cut it off at some point, that the focus of the hierarchy is on the marginal probability distributions, and that you cut it off at some point, and if you do the simplest case, cutting it off at I equals 2, with this assumption that rho 2 factorizes into rho 1, you arrive with some further assumption at the Boltzmann equation. And that's, of course, extremely interesting foundationally, that you have here again the Boltzmann equation, but not about a different object. So the Boltzmann equation here is about the one particle marginal probability distribution. Okay, and now we have this second derivation, which I call the BBGKY derivation of the Boltzmann equation, and we can ask, well, how does this equation, this derivation, relate to Boltzmann and Gibbsian statistical mechanics? So maybe not surprisingly, there isn't really a clear fit to Boltzmann and statistical mechanics. So as I've noted, rho T1 x1 is the one particle marginal probability distribution. We have no clear motivation to look at the one particle marginal distribution in Boltzmann and statistical mechanics. Of course, we can do it. There's nothing that prohibits you from doing it, but we don't seem to have a clear motivation for doing that. One is allowed to do it, but there isn't a clear link, I think, here to Boltzmann and statistical mechanics. What about Gibbsian statistical mechanics? And here I think it will depend on what is meant by Gibbsian. So if you look at some papers, for instance, I mean, in Yu's compendium, Yu has a quote that this derivation in the BBGKY hierarchy has some connection to Gibbsian statistical mechanics. Of course, David, I've just quoted here two papers, has papers where he also argues that there's a connection to Gibbsian statistical mechanics. So just initially, maybe before we go into the details, there are some suggestions out there that the BBGKY derivation of the Boltzmann equation is in a way Gibbsian. And we argue that it really depends on what you mean by Gibbsian. Yeah. So one colloquial view is that whenever you ask, or whenever it is asked, how a probability density evolves over time, this is automatically a question about Gibbsian statistical mechanics. So then we are automatically in the terrain of Gibbsian statistical mechanics. Then, of course, if you have the view that whenever you ask how probability density evolves over time, then it's Gibbsian, then of course BBGKY's derivation of the Boltzmann equation is Gibbsian, because if you ask here how a probability density evolves over time, namely the marginal probability density, the marginal, probability distribution. And maybe David's 2020, 20, and 21 can be interpreted along these lines, but not sure. I'm just saying that we have this colloquial view, and if you share that colloquial view, then of course you're automatically in the terrain of Gibbsian statistical mechanics. But I think that colloquial view, the problem is that this is of course extremely broad, and that's the next slide. But so considering how probability densities evolve over time is of course common practice in many, many areas of science that have no obvious connection to Gibbsian statistical mechanics. I mean, I could give you a long list, but of course, this, for instance, you also do in population dynamics. You consider how probability densities evolve over time. You also do that here in the dynamical systems framework. You ask whether they approach a certain probability distribution and so on. And you do the same thing in economics. Yeah, in economics, you have similar questions. And also, I think one shouldn't forget that is what I said before. In Boltzmann and statistical mechanics, you're of course not prohibited to consider how probability densities evolve. You can do that. You have microstates, put a probability density on it. Also the Boltzmannian framework can do that and does sometimes do that. For instance, in the mentaculars. So just this weak constraint where you just say, well, it's colloquial view, it's immediately Gibbsian whenever you consider how probability densities evolve, is a very weak view where you can have doubts about it, because that's done in many areas that have nothing to do with Gibbsian statistical mechanics. And in addition, there are also mismatches between BB-GKY's Boltzmann equation and Gibbsian statistical mechanics in the following sense that usually in Gibbsian statistical mechanics, you don't consider one-particle marginal distributions. They are not part of the theory. So if you did an introduction to Gibbsian statistical mechanics, one-particle marginal distributions play no role. Of course, you can consider them, but it's not that it's the core of Gibbsian statistical mechanics in any way. And also central elements of Gibbsian statistical mechanics, such as phase averaging, Gibbsian ensembles, and equilibrium don't really seem to play a role in BB-GKY's derivation of the Boltzmann equation. Also, Gibbsian statistical mechanics is really an equilibrium theory mainly, as we know. Of course, there's a non-equilibrium part, but it's first and foremost an equilibrium theory. Where the dynamics plays little role, but BB-GKY's Boltzmann equation is, of course, all about the time evolution of systems. So, before we come to conclusion, so what we will say is, well, yes, we can understand there seems to be a Gibbsian element to this BB-GKY derivation because you consider densities and how they evolve over time. And of course, in Gibbsian statistical mechanics, you also consider probability and the densities, but they look a bit different, of course, because you usually don't consider one-particle marginal distributions. And so there seems to be something that seems to point you to Gibbsian statistical mechanics, but then there are also profound mismatches. So that's what I said, the picture here is mixed. And that's what I also say in the conclusion. So let me just briefly summarize what I hope you will be able to take away from the talk. So the broad question was really, we have Boltzmann equation, the Boltzmann equation. We have the two derivations of the Boltzmann equation. We want to know how they relate to Boltzmann and statistical mechanics and Gibbsian statistical mechanics. And the broad picture I wanted to present you here. I mean, this is all based on a paper that Roman and I wrote in the special issue in entropy. So if you want to read more about that, you can read it in the paper. But concluding remarks, if you look at Boltzmann and statistical mechanics, of course, Boltzmann's original derivation has some connection to Boltzmann's statistical mechanics, I mean, by introducing local variables. Though the dynamics is not exactly the same, of course not, because Boltzmann and statistical mechanics will consider the full Hamiltonian dynamics, and Boltzmann's Boltzmann equation makes this assumption with the Stoßzahl ansatz, etc. But the Boltzmann equation can be assimilated to Boltzmann statistical mechanics. The original Boltzmannian account, original derivation of the Boltzmann equation doesn't really have to do anything with Gibbsian statistical mechanics. But you have this other derivation, the BB-GKY derivation of the Boltzmann equation, where we said cannot be assimilated to Boltzmann and statistical mechanics. Of course, one can consider one-particle marginal distributions or higher order marginals in Boltzmann and statistical mechanics, but it's not something that you naturally do normally. Then whether BB-GKY's, this is this point, Boltzmann equation can be assimilated to Gibbsian statistical mechanics will depend a bit on your interpretation of Gibbsian statistical mechanics. We voiced some skepticism. We said there's seems to be only a very weak interpretation. Only a very weak interpretation of Gibbsian statistical mechanics seems to do that job. But yeah, I mean, this is our conclusion. Maybe you have, and I'm sure you have further thoughts about that, and I will be very interested to hear them. But for now, I've talked for a very long time. Thanks very much for your attention. It was a pleasure to talk here. Thanks.
There's lots to ask that here. Let me have a couple of. Can you hear me?
Yes, not so well, but I'll try. Let's try. Yeah.
Sure. I mean, I can just speak loud.
Now I can hear you better. Yeah, that's much better. Thanks.
I was without the microphone, but let me try. How's this?
Yeah, that's good.
Okay, great. Yeah, I mean, let me make a couple of sort of related comments about the original the first part of the talk. That part. I mean, one observation was I'm not sure I want to say that the derivation has no connection to the microdynamics. I mean, Boltzmann has a particular hard sphere model in mind, so there's obviously the abstraction of dynamics that comes with that. But of course, you still, if you want to do that, if you want to say I have a hard sphere potential, you can put that into the underlying Boltzmannian dynamics. It'll be delta functional and kind of annoying, but you can do it. And conversely, there's no problem having some interaction that's not a hard sphere potential for the Boltzmann equation, and lots of more contemporary applications will absolutely do that. So it sort of feels to me as if the place in which the Hamiltonian is coming in is in calculating the cross section that then gets plugged in. I don't think that's particularly in tension with the broad aspects of what you're saying.
Can you just maybe quickly answer that already? You're absolutely right. And if you see what I wrote here, I mean, I didn't write it has no appeal, but what I wrote actually in my presentation, let me just but I wrote no direct appeal. So because of course I mean, maybe it comes from a discussion within Roman. Roman in original note, this is no appeal to the Hamiltonian mechanics. But then I said exactly what you said. No, there are assumptions in about how the Hamiltonian looks like, hard spheres, etc. But then again, the dynamics is not. It's not just that you only look at the Hamiltonian. Yeah, because with the Stoßzahl ansatz, you actually get, and assuming that it holds all of the time, you get assumptions in that are actually very likely in conflict with the Hamiltonian mechanics. So there's this kind of strange thing going on, yeah, which also makes that the derivation ingenious. But I'm absolutely with you, of course. It's not that there's no appeal to Hamiltonian. I wrote no direct because I wanted this. Yeah, and if you ask me what I mean by that, is absolutely right, yeah.
Yeah, I see what you mean there. And the other thought was, I mean, so as literally presented, on this version, on Boltzmann's version of the equation, the function rho is a sum of delta functions.
Exactly.
Not the kind of thing that can be differentiated or plugged into a differential equation. So what we have to do, and what Boltzmann does very hand-wavingly, of course, I mean, it's a brilliant piece, obviously, but retrospectively it's very hand-waving, is just sort of suppose it can be smeared. So there's some sense in which the idea is this isn't literally the phase space density, it's some averaging of the phase space density over regions large compared to the interparticle separation, something like that in momentum position. But then I think it's worth saying that if you try to do that, I won't even say rigorously, but you try to specify the details of that, the ways of doing it I know tend to end up probabilistic. So there's sort of, on at least those kind of routes, there's a sort of probabilistic component coming in. Now, as you say, it's not that the Boltzmannian can't avail themselves of probabilistic notions, but I think it's somewhat salient in thinking about the way in which the frameworks connect.
Well, I did write that in one of the slides. Where is this? Here, the number of velocities molecules is sufficiently large so that the discrete velocity distribution can be approximated by this differentiable function f. Yeah, right. Of course, absolutely right. And I said that. I mean, I think. Well, what should I say to that? I think naturally, if you talk about the exact distribution of state, we will think about Lanford theorem. Of course, Lanford theorem is much more precise, and Boltzmann just assumes that it can be smeared out and makes this derivation. Lanford, of course, is the one who in his theorem relates the two, who says if you consider the exact initial state and the exact distribution, a distribution of state, by which I mean this discrete distribution with the jumps, and then you consider a function f that is differential that is close to that exact distribution of state and evolve it forward, how do the two relate? So Lanford, the result Lanford is the one who is doing it regularly, so to speak, and Lanford then derives. So when you ask me about that, I think we will naturally come to Lanford, and Lanford, of course. I mean, Lanford, it depends on what you mean by probabilistic, but Lanford, of course, then has this result that for, I think, 1 minus delta in a small region about an initial point x. So for nearly all or the most of initial conditions, you actually get that over at least some finite time span, is 40% of collision time, you have that Hamiltonian, so you have that your distribution of states and evolved forward is the same as evolving it under the Boltzmann equation. And here you're comparing the exact distribution of state. Yeah. And you have here, maybe you want to, what you mean by probabilistic is that 1 minus delta. Is that what you mean? I'm just asking. This is what naturally comes to mind.
I mean, what I literally mean is that function f, if what it is the number of particles at a given phase space location, that function is a sum of delta functions, and it's not going to stop being a function of delta functions, sum of delta functions, however many. So again, that thing literally cannot satisfy the Boltzmann equation. So what does satisfy the Boltzmann equation? Some kind of smearing of that object. Now I don't know. I'll defer to Jos on how the Lanford's result worked. My recollection was that it's smeared probabilistically, but I might be wrong about that. But in any case, it has to be some level of smearing coming in.
I think that's an interesting question, is how you interpret it. I think you probably, if you now ask me now, you have two options. One option is probabilistically, but the other is really just thinking, well, it's an approximation. We just think a bit of an approximation of the relative frequency distribution. Yeah.
You can do that. You could Fourier transform the sum of delta functions, and then you could put some kind of bandwidth on it and get out a function that's smeared and look at that. But if that kind of thing leads you less towards BBGKY, leads you more towards something like the Morris-Wanzig framework. And I think that's perfectly viable. But again, that framework ends up being quite probabilistic. I mean, this isn't to say there isn't such a thing. I don't know a way of specifying the smearing process that doesn't have some kind of probabilistic component coming into it. Again,
that's an interesting question. I think I have to further think about it. Naturally, I would say you have two options. Either do it probabilistically, yes, but the other really just still regard it just as an approximation.
But then I don't think
more than that. Yeah. That's an interesting question. Yeah, absolutely. Yeah. Thanks for that.
Thanks for this. I think this is really interesting. Just one small footnote about whether there's a direct application of Hamiltonian dynamics or not. One thing that should be mentioned is that there is an application of the Liouville theorem that you've conserved measure, because you consider, little region dv1, dv2 around v1 and v2, and after the collision, dv1 d prime, dv2 prime, and Boltzmann explicitly proves his little version of Liouville theorem that volume is conserved, and that's important for him to write down that integral. So,
yes, thanks for that. Yeah.
That's just sort of a passing remark. It's worth mentioning. But one thing I want to ask is, so towards the end, you raised the question of whether this is Boltzmannian or Gibbsian. And I'd like to hear more about what is it that we're asking when we're asking that? And what are the rules for assigning something to Boltzmannian or Gibbsian camp? Because we're not talking about historical Boltzmann and historical Gibbs. And textbooks don't come labeled Boltzmannian and Gibbsian. So one of the reasons I'm asking is when I heard the first version of this talk in in London last year. I was a bit surprised to hear that Gibbsian statistical mechanics is an equilibrium theory, and that you're not supposed to consider evolution of probability distributions over phase space.
No, I think,
that's because the reason it surprised me is I was thinking of the actual historical Gibbs, and there's a chapter about that. But if we're not, if we're not talking about what Gibbs did and what Boltzmann did, what are we saying when something is Gibbsian or not Boltzmannian, and so what's at stake?
Sure. Yeah, I think that's absolutely, of course, a crucial question.
This.
Yeah, and it's, I mean, so it will really depend what you look at, but if you look at standard compendiums or standard foundational books on Boltzmann and statistical mechanics, such as Jo's compendium or Roman's compendium or our book, what you standardly find is this division between Boltzmann and statistical mechanics, Gibbsian statistical mechanics. Yeah, where Boltzmann is really represented as I said, with this microstates. It's this very simple idea. You have microstates, and then you have in some way to individuate macrostates, and you look at how the macrostates evolve over time. And so I think this discussion simply exists, or this division simply exists in the literature, between Boltzmann and statistical mechanics and Gibbsian statistical mechanics, where I think it's much clearer what Boltzmann and statistical mechanics is. What really Gibbsian statistical mechanics is, I mean, you can also say there are different versions of Gibbsian statistical mechanics, perfectly fine with me. Yeah, we tried to analyze that, as I said, in a BJPS paper. I think we need to be careful. I think I'm probably absolutely with you if you think that it's not interesting to talk about just some random differentiations between Boltzmann and Gibbsian statistical mechanics in the literature. But I think it's not like that. So there is, if you look at the foundational discussion, a solid agreement that we have this what's called Boltzmannian statistical mechanics, and we have what's called Gibbsian statistical mechanics. And the way I've introduced it to you with the protagonists, and what I've presented here is, so to speak, common ground, I think. But I think, as I said, what's Gibbsian statistical mechanics, there is more, at least it seems to us, from what we have talked to various peoples over the last years, seems to be more disagreement what exactly it is, lots of different interpretations. And maybe I emphasized that too strongly, but of course I know that there's a non-equilibrium part of Gibbsian mechanics. And I was just presenting the view that it's mainly an equilibrium theory, in the sense that when it's applied, it's usually in the equilibrium framework, the framework of calculating phase averages and what the system is in equilibrium. But of course, you can also consider this evolution of densities over time and coarse graining and approach to equilibrium. That's also part of Gibbs. Yeah. But if you ask me where does this BSM and GSM come, I think it's really from a division that I think is really shared by nearly all, I think, foundational writers, that there is something like a Boltzmannian framework that goes back really to the Ehrenfests, and a Gibbsian framework that goes back to Gibbs, and that has been developed over time, and that has then been called Gibbsian statistical mechanics and Boltzmann statistical mechanics. Yeah. I hope that helps.
Okay, thank you.
Yes, thank you, Charlotte. It's good to see you, and thanks for your talk.
Thanks.
You mentioned my compendium a couple of times, and maybe I am to blame for introducing or at least emphasizing the distinctions between Boltzmann's approach to statistical mechanics and Gibbs's. And one of the reasons why I put some emphasis on these distinctions was that at the time when I read all this, all the textbooks and the literature available to me, it seems like most people conflated the two and thought that, they were all equivalent and it didn't really matter what you used. But in emphasizing these distinctions, I have never intended to create a dichotomy opposing camps, or even a schism, because there are distinctions between the two, but there are certainly also areas in which they overlap, and in which the question, is this Boltzmannian or Gibbsian, fails to make sense. I mean, in the sense that it could be both.
Mm.
And I also never, I think, intended to implicate that one approach was superior to the other, or more fundamental than the other. So that's by way of introduction. But I had a question about what you said.
Let me quickly comment on that. Thanks.
Yes.
And I actually, I think I'm in broad agreement with you. I mean, you will have seen that when I presented it, I didn't say anything about that Gibbs is actually in conflict with Boltzmann, or there can be, it really depends on, I think, how you interpret Gibbs and statistical mechanics, but there's certainly one way of interpreting it where Gibbs can be practiced alongside Boltzmann and statistical mechanics, so where the two are compatible, so to speak. I didn't mean to say that they're incompatible. So I just I wanted to present it broadly and generally, so that it can be left open to different interpretations. And I think we need, what I said already to the previous question, we need to be it doesn't really make much sense to just, to essentialize Gibbsian or Boltzmann and statistical mechanics. That doesn't make sense. But what I've done here, hopefully in the talk, is to show you how the Boltzmann equation really relates to certain features which we discuss in the context of Boltzmann and Gibbsian statistical mechanics. And I think that's the interesting bit. Yeah. Okay, please go on.
Thank you. I had a question about how your reconstruction of the Boltzmann equation in terms of Boltzmannian statistical mechanics.
Okay.
And
yeah,
I think I think it was a slide earlier than that. This
one with the local and global variables, or even earlier. I mean, here we.
Let's go back to your. I think it was in the section with the main protagonist.
Okay. Yeah. Sure. This one.
No, on the Boltzmann equation.
The Boltzmann equation. Sorry.
Right. One slide back. Yeah. So one slide back, please.
Like that. Sorry. Yeah.
Yes, that's what. Yeah. So you start with mentioning Boltzmann equation and the H theorem.
Yes.
Now, you didn't come back to the H theorem.
I have it in the appendix. So.
Let me try to.
Yeah, well, maybe go back. Yeah, so I didn't because of time, but what do we have it? Sorry. I'll be here. Yeah, I go. Yeah.
It's important for me because this was Boltzmann's most celebrated result.
Yeah.
In which he claimed that he had, somewhat optimistically, that he had finally found a mechanical reduction of the second law of thermodynamics, and accordingly had found a way to show that even in a mechanical system, you could have law-like irreversible behavior.
Yes.
In the sense that gases must necessarily evolve towards equilibrium.
Yes.
And not away from equilibrium. And there has been much discussion, of course, about how he could substantiate such a claim.
Yeah, sure.
The consensus is that it's due to the Stone-style ansatz, which you have on the next slide. And sure. I want to ask you a question about that. So can you show? Yeah. So you say correctly that the Stotzel ansatz is about the number of collisions in a certain time interval in which the initial velocities are changed to the final velocities. And that it is just proportional to the number of the particles with the initial velocities. But the next line says the Stotzel is also assumed to halt in reverse temporal direction. I doubt that that is historically correct. And further,
I think we have it from your, yeah, but go on, yeah.
Further, if you do assume that the Stotzel ansatz halts in the reverse temporal direction, then you will have both an H theorem and an anti-H theorem, which imply that the H function is not changed with time, and that the system is already in equilibrium, and there is no irreversible behavior.
Maybe let me just go back, because this is actually, let me just a quick look that I don't, maybe we have described it wrongly. I'm just trying to find. So this is really we really wanted just to present here what you did in the compendium, but maybe we give me a couple of, sorry, I just have to find it, because maybe it's the wording that is misleading. I might have to get that over there, then I can find it. Let's just one minute, please, because maybe it's the wording. What I mean is something very specific here. I think maybe the wording is misleading. Let me just have a quick look, because I don't think we mean what you have just said. We mean something different. Here we have H theorem. Let's go to them. Yeah. So one moment, the H theorem. Yeah. Okay. Exactly. 29 and 30. Sorry to be so slow, but soon I have it. It's 29 and 30. I think we mean this. It is probably a bad description, and actually, so you see what we actually do here. Can you see the slide I have here? Yeah.
Yeah.
So that's from your compendium, from your wisdom. We have.
So this is about the initial velocities.
Yes.
So the initial velocities in the collision are at stake. So the number of collisions is proportional to the number of particles with an initial velocity v1 and an initial velocity v2.
So what I mean by the second one is that one, and that's why I said I think it's how it's described on the slide is misleading.
These are reversed collisions, the inverse collisions.
But this is what I meant. I'm sorry for that. I can see it here. Yeah, but this is what we mean. Sorry about it. Never meant something else. And you say now it's clear, but we just meant you need this equation, but you also need this a similar ansatz about the inverse collisions. This is what we meant and nothing else. Sorry about that. Didn't want it to be misleading, but you see what I mean. I mean, it really just meant these two, because these two, without these two, you can't derive it.
No, that's true.
And we meant two. I think this. I have to change that in the slide. The way we phrased it is misleading, but we meant that you have the so-called inverse collisions, and you need a similar ansatz about them.
Yeah, I know it's a subtle point, and it's prone to be.
The reverse temporal direction is misleading. Sorry, this was really. But what we meant is really, that's why about the inverse collisions. Yeah.
Okay. Well, thank you.
Sorry about that. Yeah, this is when you describe it intuitively. Sometimes this happens. But yeah.
But well, when you try to reconstruct the Boltzmann equation from your Boltzmannian statistical mechanics point of view, what you can do, as you correctly mentioned, I think, is that you can see that you can see the Boltzmann equation as an approximation to an underlying Hamiltonian evolution via Lanford theorem, at least for a short interval of time. But
Exactly.
as I said, the result that Boltzmann was certainly most proud of, and which he was duly celebrated by his contemporaries, was his H theorem.
Yeah.
And you cannot get that out of the Hamiltonian evolution.
Yes.
Not even with Lanford's approach. Because,
Just showing that slide about, absolutely. Yeah.
So there seems to be a wider gap between what Boltzmann tried to do in his 1872 papers and the Boltzmannian approach of 1877. And it's remarkable also, I want to say that maybe it's wrong for me to try and bringing the historical actors as when you and David emphasize so much that what they do is what they try to present is may have no resemblance with the historical figures of Boltzmann and Gibbs. But when Boltzmann wrote his book on gas theory in 1906, it is mainly from the point of view of the Boltzmann equation. And the whole construction of these macrostates is just relegated to a paragraph which he says this is just a mathematical the mathematical and expanding on the mathematical meaning of H, which suggests that for him this is not the central result of the theory.
Yeah. I mean, here you come into, of course, that you then later Boltzmann acknowledges that this can't universally hold the H theorem and that you need something like probabilistic interpretation. Yeah. And then you can ask how the probabilistic interpretation relates to Lanford's theorem, etc. Absolutely, yes. I mean, I just agree with what you said. I mean, we didn't focus so much on the H theorem because also of time and also, of course, because the focus was on the Boltzmann equation and a bit less on the H theorem. But and all you say is absolutely right. I mean, the celebrated result was, of course, the H theorem, and from the H theorem, you have then this discussion about as the discussion moves forward, that it has to be in some sense in conflict with the Hamiltonian dynamics, and you need a statistical interpretation, etc. And then you can discuss how Lanford relates to this, etc. Yeah, I think agreement with you. Thanks for that.
Thank you. This is really helpful. So my question is related to Wayne's original question. I will talk more about this tomorrow, but right now, what I take to be the debate between Boltzmannian and Gibbsian is that at least some Boltzmannians do not take probability distributions to be the object study of statistical mechanics, right? They don't accept probability distributions can describe or represent systems in such a way that probabilities can evolve over time, right? I think I heard one Boltzmannian once describe probability distributions are not physical and they don't live in our physical space-time. So it doesn't make sense to say probabilities can evolve over time. So my question for you is, as a Boltzmannian, do you accept that probability distributions can describe or represent the state of systems, which can involve time? And also to add on to, since you were talking about how Boltzmannians and KGBY's Boltzmann equation are about time evolution of systems, and I take the disagreements about Boltzmannians take timed evolutions of systems, the systems here are actual individual system. While for Gibbsians, we're talking about time evolution of probability distribution. So do you have a take on this? Thank you.
Yeah, thanks. Well, I think we need to be careful not to trying to essentialize that there is this Boltzmann account out there, or Boltzmann statistical mechanics, or that's Gibbsian statistical mechanics. Yeah, I mean, I know there is this discussion about out there to what extent Boltzmannian can really even accept probability density and probability distribution. So I would be much more cautious. I mean, I would say, well, so the framework I've presented to you is picture of Boltzmann and statistical mechanics with microstates. So this is the basic framework, let's put it like that, framework of Boltzmann statistical mechanics. But I wouldn't, so that's why I have this slide here. I wouldn't say that there's anything in Boltzmann and statistical mechanics per se that prohibits you to consider probability densities. I think, why not? Yeah, this goes a bit also question of your question. Does Boltzmann and Gibbs always need? Can they be together true? I think in some cases both perspectives might be consistent, and might be fruitful. I mean, it really depends on what exactly these perspectives are. But I wouldn't go so far and say that Boltzmann and statistical mechanics doesn't allow you to consider probability densities. No, I would say, well, the basic framework is the one I presented to you with the macrostates and our initial states over time. But of course you can ask, I mean, and it has been asked in papers out there. For instance, you can ask, well, what if I now have a probability distribution that describes the probability of preparing the system in a certain state, in a certain microstate? How then, this you can also consider under Boltzmannian perspectives. Then you can say, well, then you have this microstate, you have a probability distribution over it. They evolve into the equilibrium macroregion, given this initial probability distribution of describing the system in a certain state. I think you can do, and it would be in a way odd to prohibit you doing that from the beginning. That's why I said I wouldn't prohibit that. I would say, well, for Boltzmann, you're also allowed to consider probabilities. Albert, in the Mentaculus, you consider probabilities. So there are definitely many discussions of Boltzmann and statistical mechanics out there that are clearly Boltzmann, and in the way I've presented it, where one also talks about probabilities. So for me, it seems a bit radical to say, well, no, it's Boltzmannian, you shouldn't consider probability distributions. I would say it's not. So if you can present the basic features, it's about microstates and how they evolve. It's not that you automatically consider probability densities, but then if it's a bit a Boltzmann account that is a bit more specific in the Mentaculus, or if you want to consider probability densities that describe the initial distribution of state, you can also consider probability densities and probability distributions in Boltzmann. This is what I would say about that. But of course, then, I mean, this is what I said. We have to be careful not to essentialize this what Boltzmann and Gibbsian statistical mechanics is. I think what's interesting and what I tried to do in this talk is to clarify conceptually how certain distinctions relate. Yeah. This about and of course, someone can be a defender of Boltzmann and statistical mechanics of a specific version and say, but for me, part of that account is that it's not allowed to consider probabilities. That's maybe one version of Boltzmann and statistical mechanics that one can defend, but I wouldn't go so far, as I've said. And about the probability distributions and how they evolve the non-equilibrium part of Gibbsian statistical mechanics. Of course, I mean, there is this discussion about Gibbsian statistical mechanics and how probability densities evolve over time, and how whether they evolve to the goal sometimes is that they evolve to the stationary distribution. And there is some resemblance in the sense that in the BB-GKY derivation, you also consider density and ask how it evolves over time. But again, the BB-GKY density is, of course, a one-particle marginal. That's usually not considered in the Gibbsian considerations. But yeah, so in that sense, it seems to be a bit different. So I hope that, I'm not sure whether I clarified or answered all your questions. If there's still something left, then let me know.
Oh, this is helpful. Thank you.
Last question by Isaac. We have a bit of flexibility here. But...
Thanks very much. That was really interesting. So at one point you said that the Boltzmann equation I think you said approximates the Hamiltonian dynamics, and I just didn't quite follow the line of thought there. So I was just going to ask if you could.
Yeah, and this is again an intuitive. Let me see, where do we have it? Sorry. Yeah, the dynamics. Yeah, I mean, the thing is, I mean, it's difficult to talk about this, and I try to talk about it intuitive, and I said that it's an approximation. I think most sense this makes probably when you look at Landworth's theorem, because here you see how the Boltzmann equation approximates really how the true Hamiltonian dynamics. What I really wanted to say about it relates a bit to what Jos said, is of course the Boltzmann equation, with all the assumptions Boltzmann made in his original derivation, and then with the H theorem, you of course know that this can't be strictly true. This is in conflict with Poincare recurrence, time reversal invariance, etc. So what you arrive at is a statistical interpretation of the H theorem, but this then demands a statistical interpretation of the Boltzmann equation. So you know that the Boltzmann equation the original Boltzmann derivation can't be 100% true. So it can only be an approximation, or an Boltzmann equation. One can try to approximate the true Hamiltonian dynamics for a particular sort of time, but not certainly forever, because we know that this doesn't work. I mean, this is what I meant. I mean, I tried to put informally in words what I summarized now, that we know that the original Boltzmann derivation can't be a true description of what's going on for all the time, for all initial conditions. And so the dynamics is different in the Boltzmann equation from true Hamiltonian dynamics. We know that. And so at best, it can be an approximation, I think. I hope that makes sense. This is what I meant.
Thanks.